we are now on the last part of Core Pure. I think this is the very last bit that you've got to do, actually, isn't it?
Yeah.
So we're at the very, very end of Core Pure 2. This, though, for us, will go into FP1's transforming differential equations. I'm just finishing putting that together now. So we're going to be doing something called coupled first-order linear differential equations. Okay, well, we understand what a first-order linear differential equation is. It's a differential equation that has just got linear coefficients. But coupled means that the differential equations are linked to each other. So your differential equations are going to be a mixture of different variables. So I'm going to just talk about a particular scenario that we've got here. And it says that in biology, Lotka-Volterra equations, also known as predator-prey equations, describe how two species interact in terms of their populations. And for those of you who did the UCL project, you'll have probably remembered lots of these things about about population modelling. This is basically a population modelling kind of scenario that we have here. Suppose that there are X bears and Y fish. The population growth of bears, which is dx dt, remember we're concerned about whether this is positive or negative. It is going to be related to AX. So AX is related to some factor about the number of bears that are currently there. So clearly, the rate of the population growth of bears is going to depend on, and more specifically is proportional to, the number of bears. So if there are lots of bears there, that might mean that it's going to be leading to more baby bears, okay? It's also going to be proportional to how many fish there are, because we know that the populations of bears and fish in this scenario are going to be related to each other because the bears eat the fish. So it's also going to depend on some factor of y, which is how many fish there are, because it depends on how available the prey is. If there's more fish, then there can be more bears because there's more food for them to eat. But then I've also added in a different function. This function is of time. So notice how this is a function in x, this is a function in y. You can have an extra function if you wanted to, because there might be something else that's going on that's not to do with bears and it's not to do with fish. In this case, it could be something about how much bears breed in the summertime, when they don't breed very much in the wintertime. So you might want to factor that into the model. You're then going to have the same thing to do with the population growth of the fish. It's going to be related to how many bears there are, because if there's more bears, there's going to be a greater fish decline. It's going to be related to how many other fish there are, because if there's more fish, then there can be more breeding that can happen. And again, there might be some other time-dependent factor. So this word coupled that we have here is because the rate of change of bears is mixture of x and y. It's no longer in one single variable of things to do with x and things to do with time. It's coupled with this other differential equation here, which is a mixture of y's and t's, but also x as well. So they're two sets of equations that are dependent on each other. What could you tell me about these different variables that we have, a and b here? Why they might sometimes be negative or why they might sometimes be positive? Can we think about what this coefficient here, c, might be for the population of fish if we're talking about how many bears there are? Is it likely to be a positive number? Is it likely to be a negative number?
Positive, that means it's adding to the population for now.
Yeah, I think it's possibly likely that this is going to be a negative number, because if x was a high number, if there were lots and lots of bears, the rate of change of fish, we should probably expect that that would then be making that become negative. Not necessarily overall negative, but it would be restricting the growth of the fish population because there are more bears who are more likely to be eating those fish. Okay? So that's just sort of some of the ideas that go behind this. This next slide here with some different graphs is 100% not on the curriculum, but I wanted to show it to you, particularly because I know some of you had done the research on this before, okay? So these top two are population models for the fish and the bears, or in this particular case, we've got wolf population and moose population. This one is a rabbit population and a fox population, and they are with time along on the bottom axis. So you can see here that when a particular population is going up, so when the wolf population is increasing, what can you see each time the wolf population is increasing? The moose is, yeah? The moose's population is decreasing. And then you can see when the moose have decreased a lot, in other words, the wolf have eaten so many of the moose, when there's not many moose left to eat, then the wolf population also declines because there's not so much food around. And you get this pattern of these things sort of going on over time like this. And you will have looked at this when you started doing your population modelling all that time ago. Yeah, these would be like cyclic population ones. And ours might do this kind of thing. You can get an idea of what things might create cyclic stuff. When you're solving the differential equations, you might imagine there to be something with sine and cosine in there that might create that kind of pattern. Or they might not do that. They might completely die out. The populations might go starting up here and they might just go straight down to absolutely nothing. So again, like, this isn't on the curriculum, but I think it's worth us to kind of look at some of these things. So these two down here, these are actually some of the things I'm studying at the moment in my degree stuff, which I thought was interesting to talk about. These ones are about solving differential equations with different starting points. So this one down here, I can't remember what I was modelling, but it was, I think it actually might be what we've got on the next page. I think it is actually this one that we're about to do here about fish and bears. These ones tell you, depending on how many, this axis along the bottom is the number of bears, and this is the number of fish. Depending on how many number of bears or fish there are to start with, these tell you how the populations will change. So notice this one was time and then populations along the side. This is population of one of the species, population of the other species, and the arrows represent what happens over time. So it's kind of got like an extra dimension to the graph. If something starts off in this particular point here or anywhere along this line, so if the population started with, I don't know, 400 and 400, it's likely that the population is just going to keep going up in quite a linear kind of way. If the populations started somewhere over here, maybe there was, I don't know, 300 of the one on the x-axis and only 100 on the one of the y-axis, you can see that the population is going to follow this kind of trajectory, and eventually the population like crashes out like that. So these are what we call phase portraits, and it's something that you'll look at university to try and predict what happens in systems depending on where things start from. You can also say this is just another version of this kind of thing. If a population started somewhere over here, over time it kind of loops around and it spirals until it kind of settles on a particular fixed point. I just thought it was interesting because this is actually the stuff I'm studying. I'm doing these Lotka-Volterra predator-prey models, but I'm looking at like where are the stable points in the population and where is it that the populations will kind of go crazy and will never return to normal, okay? So that's just something to look forward to in your futures. What we're going to do though, we won't really be doing any of this stuff with these graphs. We're going to be trying to think about actually just how we solve these coupled differential equations that we've got here. So here, this is the definition of what they look like. They are homogeneous if f of t and g of t are both equal to 0. In other words, if they're not there, okay? You know that if they're homogeneous when we had them previously, they were equal to 0. These are the sort of like the bits that created particular integrals that made it a non-homogeneous one. So we still use that same language about homogeneous and non-homogeneous. Now, these look like they could be difficult to solve, but they should also remind you of something else that we will have seen way back when you were probably doing like year 10 kind of maths. What kind of thing might this remind you from like year 10? Simultaneous equations, okay? So these are basically like the most grown-up version of simultaneous equations that we've got, okay? Usually with simultaneous equations, we just had two variables, x and y. But in this set of simultaneous equations, we've really got x, y, dx dt, and dy dt. So we just have to think about how we go about solving that set of simultaneous equations. So let's read this question here, and then if we want, we can look at the strategy, or we can look at the strategy afterwards. At the start of the year 2010, a survey began on the number of bears and fish on a remote island in northern Canada. After T years, the number of bears x and the number of fish y on the island are modelled by the differential equations. dx dt is 0.3x plus 0.1y, and dy dt is minus 0.1x plus 0.5y. And we're going to try and show that you can have this differential equation here being equal to 0. Just tell me some obvious things that you notice about this differential equation that you've got here. It's a second order differential equation. Tell me something else about it. It's a quadratic type thing, so we'll know how to solve that. But can you just tell me about the variables? It's equal to 0 as well, but what about the variables? They only have x, okay? So because it only has x, that means that we need to eliminate y, okay? So the way we're going to do this is we're going to take equation 1 and we're going to make y the subject. Because if I can make y the subject, I can substitute it in here, and then I've got this whole thing over here is in terms of x. But then I've got a dy dt. How can I get rid of the dy dt? No. If I've made y the subject here, and I want to get dy dt, yeah, good. I can make y the subject and substitute it in here. Then I can differentiate this one that has y as the subject, and I can put it in here. And then everything in this second equation will have eliminated x, and we will then have the whole thing in terms of y. And that's what this strategy says up here. It says make y the subject of the first equation, then differentiate it to find dy dt. And then you can substitute the y and the dy dt into that second equation that we've got there, okay? So I'm going to do that for this first one that we've got. Now, if you wanted to, you may find doing these questions a little bit easier writing like this, instead of having to constantly write out dx dt equals. If you prefer, you could write good. Now, you may not want to do this, but for this particular one, because remember the dot means with respect to time, it can actually save you a bit of time writing it as x dot. So we get x dot equals 0.3x plus 0.1y. So if we make y the subject, we would have x dot minus 0.3x equals 0.1y. So we get 10x dot minus 0.3, thank you, minus 3x equals y. And that's the first one that we've got here. Now I'm going to differentiate this with respect to time. When I differentiate 10x dot with respect to time, what do I get? So that's 10x double dot, because it's x. This is dx dt, and we're differentiating it with respect to time, and it's the second derivative with respect to time. You don't have to use the notation I'm doing here. If you want to do the whole thing using dx dt, I'm very, very happy for you to do that. I just think this can be a little bit simpler. What does 3x differentiate to with respect to time? No, with respect to time. We're differentiating with respect to time, not with respect to x. Yeah, it's just 3x dot. And then y differentiates to y dot. Because remember, we're differentiating with respect to time, not with respect to x. Okay? So we've now got this thing and this thing. And we're going to substitute it into our second one. So this was the other one that we've got is y dot equals minus 0.1x plus 0.5y. So that means I can substitute the y in here and the y dot in here. So you get 10x double dot minus 3x dot equals minus 0.1x plus 0.5 multiplied by this. 0.5 10x dot minus 3x. What do we need to do with that now? Take it all to one side. So we're going to have 10x double dot. I've got minus 3x dot, and this is a minus 1.5x dot. Have I done that right?
No, it should be 5. So minus, it's a 5x dot.
That should be a, where should be a 5x dot?
No, like expand the bracket.
Oh yeah, sorry, I'm looking at the wrong thing altogether, aren't I? So that's a 5x dot, so I'll be minusing 5x dot, so I get minus 8x dot. And then I've got 0.1x minus 1.5x, so when it comes to the other side, I get plus 1.6x equals 0. And then it looks like from what they've done here, what do they want us to do that's slightly different? They want us to divide by 10, so we get x double dot minus 0.8x dot plus 0.16x equals 0, bless you. And then, because they wanted it written like this, bless you, I'm probably going to just put it back into that form. So I've got the second derivative of x with respect to time minus 0.8x, the first derivative of x with respect to time, plus 0.16x is equal to 0. So it's like a posh, grown-up version of simultaneous equations. What do you think the advantages are of using the dot notation?
It's quicker.
It's quicker. What do you think the disadvantages are?
You might
It's quite easy to make a mistake, like you saw me just doing there, but I do think, I also think that these things look really similar. Like when I look at these as well, they hardly look that distinct from each other. So, you know, just try out doing some questions one way, some questions another way. You can really only use the dot notation though, if it's with respect to time. If it's not with respect to time, you should use like a dash notation to show that it's been differentiated with respect to something else, okay? Okay, so we've done part A of the question. It then says find the general solution for the number of bears on the island at time t. What do I need to do now? Yep, I just need to actually solve this equation. So this was my part A of the question. Part B of the question is now actually to solve this. So the auxiliary equation is m squared minus 0.8m plus 0.16 equals 0, which is that m is equal to
0.4.
0.4. It's a repeated root.
Or 2.
So the I don't actually need to do a complementary function here, do I? Because it's already equal to 0. So I can actually go straight into the general solution, which is, are we talking about x or y? X. So we get x equals what?
A plus b t brackets e to the power of 0.4t.
Good. So that's the general solution of what this one is equal to here. Now we want to find the general solution for the number of fish on the island, okay? So just put a little line under there so I've got some space. So we're now going to try and find out what part C is. Now the temptation might be to go back to the beginning again and do the same process that we did up here, but to eliminate x in the other one. But we don't actually need to do that, because normally with simultaneous equations, when you think back to GCSE, you would get one of the solutions, and what would you do with that solution? Exactly, you'd sub it back into one of them. So I know what x is equal to. What else could I possibly find out from this?
What's the XDT is?
Good, so I now know what x is, and I know what dx dt is, so which equation will I use? The first one, which is the one that we haven't actually used yet. So it's exactly the same as simultaneous equations. So I know that x is equal to this. I'm now going to find out what x dot is. When I differentiate this, I get 0.4 a plus bt e to the 0.4t plus b e to the 0.4t. So then what I'm going to do is I'm going to take the x dot, in fact, why don't I write out the equation that we're going to be using. We're going to be using that one at the top. So we're going to use the fact, we're going to use number 1, which says that x dot equals 0.3x plus 0.1y. And I'm going to substitute my x dot in here, and I'm going to substitute my x in here to find out what y is, and that's going to save us some time. But I think before I do that substitution, I'm probably going to rearrange this. I just think it's going to be easier. So looks like y is going to be equal to 10x dot minus 3x. Agreed? Just rearranging that to go to this.
That's in pi, yeah.
And it's going to make sense that x and y are both to do with e to the 0.4t because they're the same populations, so it makes sense that they're kind of described in the same kinds of rhythms as each other. So we just get that y is equal to 10 lots of this, which I'm just going to go straight in with this. I'm going to multiply this by 10. And I'm going to multiply this by 10. And I'm going to subtract 3 lots of this. And so when you can see that these are going to cancel, so we just get a plus bt e to the 0.4t plus 10b e to the 0.4t. So that's our population of the fish. And this one over here was our population of the bears. So at the start of 2010, there were 5 bears and 20 fish on the island. Use this information to find the number of bears predicted to be on the island in 2020. So, what do you think that's actually asking for us to do here? Just sub in some values that we've got. So the values that they seem to have told us is that when x is... No, t isn't 10 actually, because 2010 is when the model started. So we've got x is 5, because there's 5 bears, y is 20, and t is 0. So I'm going to just substitute 5 into this one, and 0. So I get 5 equals a. And when I do it with this one over here, I get 20 equals a plus 10b. So you get 15 equals 10b. So b equals 1.5. And we want to know how many bears there will be in 2020. So bears in 2020, t is equal to 10, and we want to find out how many bears there are. So the number of bears is a plus 1.5t e to the 0.4t. So the number of bears is 5 plus 1.5 times 10 e to the power of 4. So what is that? Let's get that as a number. Which is 1,092 to the nearest bear. So we predict that there'll be 1,092 bears from 5 in 10 years.
So when you combine to get the second order differential equation,
Yes.
how would the axis work?
How would what work, sorry, though?
Because x is the number of bears, right?
Yeah.
So how would the fish affect the graph? Because the x-axis is the bears and the y-axis is the time.
So if we're looking at any of these graphs that we've got here, I don't think it's going to be a cyclic model. And I'm going to tell you why it's not going to be a cyclic model in just a second. Okay, part E, and then I'll come back to this page to answer your question. So part E of the question says, comment on the suitability of the model. So let's just have a think for a second. This is what the population of the fish is. This is what the population of the bears is. Now, when you talk about model suitability, what can we often think about doing with the value for t, or the variable t? What can we do with that? Make it really big, because we want to find out how well is this model going to last for a long period of time. What can you tell me about this if t becomes large? If t becomes large, yeah, you get like e to the power of... Yeah, if it was negative, it would tend to 0 and the populations would die out. So the population of the bears is going to keep growing. The population of the fish, what's going to happen to the population of the fish? It's going to also keep growing. Does this seem like a suitable model? No, so we need to say that. We need to say for part E of the question, as t tends to infinity, the population of bears and fish also tend to infinity, i.e. the populations keep growing. This is unrealistic, and they might ask you to improve the model. This is unrealistic. The model should take into account other factors I'm probably not going to say like death, because actually that might be taken into account by like how many fish there are, or how many, those some of the death might be accounted for. But what's something that hasn't been taken account for?
Illness.
Pardon?
Other species or
Yep, great. So we haven't taken into other factors like other species, illnesses or disease. Anything else?
Birth of new bears.
So the birth of the new bears has sort of been taken into account by how many bears there are. Can you think of why can't the population grow forever?
Limited resources.
Limited resources. Hasn't taken into account resources available. What do you mean by a resource?
Like, the fish need something to survive, right? So they eat, let's say, plants, but there's not infinite amount of plants.
Okay, good. So resources available, like fish food.
Well, at the rate we're going, no.
Any other resources? Like why can't, imagine that the population of the fish in the river has just kept on growing forever. Tell me about the river. Not enough space. Okay, so that's another one. Resources available, and also
habitat.
I do try and listen to Nahid. Like I do try and like lean in to hear what you say. Space available is a classic one, because you can't have this small island in Canada that's going to have like 8 million bears in it, because the island will be taken over. So if we know that the population is going to grow forever, is it going to look like either of these two? No, it's not going to look like either of these two hit. Now, this is actually the graph that we had. The one running along the bottom is the bears, and this one is the fish, I think, because it's X and Y. Yep. So we said, how many fish were there to begin with? Bears and fish. We said five bears and 20 fish. So it was 4 times the amount. So it's actually not going to be included on the graph here. But I guess we could do it differently. I guess we could just do, it's got to be 4 times the amount. So if we started at 200 bears and 800 fish, can you see what's happening to the arrow path? It's just going whoosh. It's just going to keep going forever and ever and ever. Okay. But if we had lots and lots of bears and not many fish at all, you can see very quickly the bear population is the bear population and the fish will decrease, and that model then no longer works, because it's going to then go into the negative fish kind of area. But there are certain, these are called phase portraits, there are certain phase portraits that look like this, that have kind of looping and going around and round in circles until they settle on something. This is obviously not in the curriculum, but any predictions of what the graphs might look like, these graphs might look like for something like this that is going in loops and going round and round?
Just be a circle.
Yeah, it's going to look like a damped harmonic motion, because we know that circular motion is a combo of sine and cos, because we've got things going up and down and moving round and round. So this is actually a type of like damped harmonic motion. You can also do these portraits for things like pendulum swinging, which is obviously harmonic motion. And what you see happening is that it settles onto a particular thing. This thing that it settles on down here would be the stable population. So wherever you are in the, however many, this isn't the one for the fish and bears, but in this imagined situation of fish and bears, wherever this population began, it's going to follow this pathway, and then eventually it settles down on a stable population where that's just what the population ends up as. So this is a really cool area of maths that isn't just about populations. It can be applied to many, many different things that we can't, we want to try and make predictions about in the long term. Anyway, we're going to just do one final example of this. And then you're going to just do practice for the whole rest of the lesson for me, okay? So 2 barrels contain contaminated water. This is one of those questions that we're going to read all of this and it's just completely pointless, so let's not worry about it too much. At time t seconds, the amount of contaminant in barrel A is x millilitres, and the amount of contaminant in barrel B is y millilitres. Additional contaminated water flows into barrel A at a rate of 5 millilitres per second. Contaminated water flows from barrel A to barrel B and from barrel B to barrel A through 2 connected hoses and drains out of barrel A to leave the system completely. The system is modelled using the differential equations here. I mean, we can sort of get a sense about what's going on in here. The amount of contaminant in A, there's 5 millilitres going in every second, and it looks like it's some kind of proportion to how much is in the Y barrel, and also some of it is leaking out of the X barrel. And you've got the same thing for the second one that we've got here.
So this ain't homogeneous, is it?
This one is non-homogeneous because of the 5 that we've got there, okay? The homogeneous ones are the ones that I'm studying a lot more at uni, because you can apply matrices to them and you can spot all the patterns, okay? So what do you think is different about this question? They want us to show that it's equal to this differential equation that we've got here. Yeah, exactly. They first of all actually want you to get it in terms of y. So because they want it in terms of y, we need to find out what x is, differentiate it, and then substitute it in. So what we're going to do is we're going to use equation number 2 to find what x is and x dot is. So equation 2 is y dot equals 3 over 70x minus 4 over 9y. So we get y dot plus 4 over 9y equals 3 over 70x. So you get 70 over 3 y dot plus 280 over 227. Does that simplify? Plus 280 over 27y equals x. Then I'm going to differentiate it with respect to time. Get rid of that. So you just get 70 over 3 y dot dot plus 280 over 27 y dot equals x dot. And then we use these two friends here into this one up here. Whoops, that didn't go how I planned. Because this area of the board always makes like a weird kind of thing. Okay, so I'm going to substitute into equation 2. Into equation 1, sorry.
You want to make y the subject first?
Yeah, it's probably, actually, that's a good idea. It might be easy to make.
Doesn't matter.
No, actually, for this one, I think we just want to dive in because we're going to want to make it look like that in a second. So we get dx dt is this thing down here. So that's 70 over 3 y dot dot plus 280 over 27 y dot equals 5 plus 4/9 of y. Oh, that's the one we want to leave, don't we, silly me? Because we want it in terms of y. Minus 1/7 of x, which is 70 over 3 y dot plus 280 over 27 y. I'm just going to take my time with this because it's going to be easy to make a mistake. Whoops. Dividing it by 7. And then we'll get it all on one side, and then we'll do some division in a second. So we get 70 over 3 y double dot. And we've got 280 over 27 plus 10 over 3 plus 370 over 27 y dot. And then we've got here 40 over 27 minus 4 over 9 plus 28 over 27 y equals 5. And then times everything by 27. So we get 630 y dot dot plus 370 y dot plus 28y equals 135. And if we're going to be really fussy, because they wanted it in that form, I actually don't think it would matter. And then I'm not going to solve that. Okay?
It doesn't even ask you to solve it.
No, it doesn't, but I'm not going to... This is basically the new part of this topic. It's the simultaneous equations. And what's different about this second order one?
It's either homogeneous or whatever.
It's non-homogeneous.
It's not equal to zero.
Yeah, it's not equal to 0. So you're going to have to do auxiliary equation, complementary function, particular integral, general solution, and if they gave you enough information, particular solution. Okay?
So if we had like a, let's say, cause for the population one, they're taking into account another factor basically.
Yes. So there's something else that's being taken in. If that's not there, the 5 isn't there, then it's always going to be a non-homogeneous one. If the 5 is there, then it could be either. Because the last page we had, I think it was homogeneous, wasn't it?
Yeah.
Yes.
When do we use the second equation instead of the first one?
So if we wanted to, what we would eventually do with this is we would come up with a general solution that is y as a function of time. You would then differentiate this, and you would take y and y dot, and you would put it in.
Actually, you know how before we did the other way around? We used the first equation and then the second one.
Oh yes, sorry, yeah. So to find now, this is what we do to find x as a function of time, because we've already used equation 1 here. You would have found out y as a function of time because it's the general solution or the particular solution. You would differentiate it to find whatever its derivative is, and you would take these two things here and you would sub into, well, we've already used equation 1, so we're going to use equation 2, because you'd have dy dt and you'd have y. All you'd need to then do is rearrange it, and it would give you what x is without any further differential equation solving that's required. Okay. Now this strategy is something that has just made quite a lot of sense right now. This strategy we've got written here, but it can be quite easy to forget which is the one that we're substituting into. So it might be something that you want like on a flashcard, or something that is just like, I'm just going to memorize how to do this bit, and once you've done a few of them, it's just then going to become pretty straightforward. Okay, but it is basically, if you can think to yourself, it's like the grown-up version of simultaneous equations, and if you know what you're aiming for, that it's all in terms of x, get rid of the things that are there in terms of y.
What does the bulk of the marks come from? What part?
So I'll show you actually, because we've got a few exam questions that are on here. So here's one about foxes and rabbits, and again I've drawn one of these phase portraits for you so you can see what happens to the populations here. They're going to be pretty like that. So it's only 3 marks for doing the simultaneous equation part of it, and then you get 4, 5, 6, 7 plus you get 14 marks for doing stuff that we already know how to do. Okay, so we already know how to do this. This was the new stuff from today's lesson. So
And they'll always give you...
no, they won't always give you that. From what I've looked at, I don't think that they always give you that. Actually, they do give you it to here. So it's just 3 marks to doing this bit. And then here you've got 6, 8, 13, 14 marks again for just doing stuff you already know how to do. So don't look at this question and be like, oh, God, I hate these ones. I'm not going to do it. Just be like, okay, well, I'll differentiate one of them and I'll do some of it. You might not get 3 marks. Maybe you've got stuck for some reason, but you can guarantee do those 14 marks down there and make sure you get those as well. Okay? I will just put those mark schemes up for those questions now, actually. Just in case you ever look back at these, you've then got the mark schemes that go with. So you can pause that. Okay, guys, all good?